Hey man, I just picked up this new bike. What do you think?
That's an awesome bike. Did you have a chance to tune your suspension yet?
What exactly does that mean?
So mountain bikes have complex suspension that requires you to set it up for different trail types.
So how do I know when it's tuned correctly?
A group of mechanical engineering students at NAU has created a mathematical model to help you accurately adjust your suspension for each different trail type, as well as we created a device to help you adjust your suspension on the trail.
Wow man, I'll be definitely using that in the future.
Have a good one.
You as well.
My name's Eric Abraham, and I'm the NAU mountain bike suspension Capstone team leader.
My name's Dylan Klemp, and I'm the client contact.
My name is Jacob Kreider, and I'm the document manager.
My name is Tyson Spencer, and I'm the budget liaison.
My name is Suleiman Al-Sinan, and I'm the co-website developer.
Hi, I'm Austin Coyne. I'm the co-website developer.
Hey man, how's it going? I saw you at the shop the other day. How's your bike feel?
Good man. I use your guys' mathematical model to tune my suspension system, but I was more wondering on what's the science behind it.
To answer Jake's question, let's delve into our Microsoft Excel mathematical model. The model describes ideal suspension settings for our test bike, a 2020 RIP9 RDO, and encompasses the 5 nationally recognized trail types: white circle, green circle, blue square, black diamond, and double black diamond. Each trail type gets its own sheet in the model. The table on the left pulls rider mass from the shock setup sheet. It also calculates or lists input values for our driving spring mass dash pot differential equation, which is calculated for the front fork and rear shock independently. Weight bias data are incorporated as a trail grade and ascending versus descending distinctions. The graph generated for each trail type is displacement at 100 Hz over a 1 second interval.
To make the mathematical model more user-friendly, we created the shock setup page seen here. This shock setup page includes 3 user inputs, which is the rider's weight in kilograms, whether they are ascending or descending, and then the terrain type. With this, the model will output the initial shock settings, which is pressure, and then their initial rebound and compression settings, and then it will also give adjustments based on the terrain type. The adjustments in our mathematical model are based on the damper value, which is the mass flow rate of damper fluid through the shock. These values are then related to various clicks of rebound and compression on the bike. To ensure our mathematical model is valid, we used a Motion Instruments linear potentiometer that attaches to our fork and shock as seen here, and then it uses Bluetooth to connect to our phones. This app can tell us different data points, such as the speed that the compression and rebound are coming back, and then also the amount of travel that we're using. This helps us optimize our mathematical model. So we performed a couple of different tests. We did a blue trail test where we set up the shocks to our settings that our mathematical model outputted. So we changed the rebound and we changed the air pressure to ensure our mathematical model was outputting the right data. And then we did 3 different trials. So we did one with the correct blue trail settings, we did one with black diamond settings, and then one with green circle settings, and then analyzed the data to see which was the best performing system. And it turns out, as you can see with this graph on the right, this was our blue trail setting. The 2 lines are parallel, and then they're also really close together. So this means that the system is optimized. And non-optimized graph would look like this, which is the black diamond trail test. And we can see that the lines don't line up quite right, and they're a little bit off. So we know our settings are correctly outputted.
Hey guys, I just finished up on that trail, and I used you guys' mathematical model to adjust my suspension settings. But as I was riding through different terrains, I had to keep getting on and off the bike to adjust it. Do you guys have anything for that?
Well, actually, along with the mathematical model, our team made a physical device that mounts on your bike, and it would allow you to change the settings while riding.
To begin this year for our Capstone project, we are focused mostly on the mathematical model that takes into account terrain types and rider characteristics. We decided that we wanted to go into second semester and tackle designing a physical prototype that could be mounted directly onto the bike for us to change suspension settings while we're riding. We use CAD modeling and 3D printing along with our mathematical model outputs to create this device.
After going through the design process, the team decided on a mechanical device that works similar to the shifters on a mountain bike. A user will be able to select what terrain type they're on using a selector switch mounted close to the handlebars on the mountain bike. This will change the suspension settings on the shocks using a cable. The cable is wrapped around the rebound and compression knobs on the rear shock, then attached to a spring to keep it in tension. As the user goes up through the different terrain types, the cable will turn the rebound knob and eventually pull the compression knob to lock out the shock.
We would like to thank our professor, Dr. Trevis, and our client, Brandon Lurie, for all their support and guidance throughout this semester.
And we'd also like to thank Peter and George at Niner Bikes for providing us with this bike to test with and prototype with all semester.
Thanks for watching our video. We hope you enjoyed our project as much as we did.